So is everyone at that point now? Okay, so you see we have a linear function, etc. So let's go back to our questions and see what we can analyze and what we can interpret with this data. Okay, so now we're on the question, determine the slope of the line, right? What does the slope represent? Okay, so determining the slope of the line, we had just discussed, okay, you need 2 points. So look at your graph and pick 2 points on your graph or on your line of best fit that are reasonably spread out, but not an actual data point. So you get to pick 2. We can pick different ones, it doesn't matter. Whatever you pick, write out the numbers. And then write out your formula for slope. So the 2 that I picked, so one of my points is 36 and 38, and the other is 6 and 6. You could have different ones than me, and that's okay. But regardless of what we pick, we should get approximately the same slope, theoretically. So as you do your calculations, I'll just do mine on the board, but you can have slightly different ones than me, and that is okay. So when I calculated mine, I got about 1.06 repeating beats. So if you got like 1 or 1 point something, did you get something about that? Something pretty close to that? If you got a little bit off, that is okay. You know, if you have different numbers than me, that is okay as long as you have about the same slope. So I'm using the symbol M to represent slope now. Do you see that? Okay, I'm using the symbol M to represent slope. So I'm going to just round that off to 1.07. And, oops, I missed something. This should be beats, and below is seconds. So my unit should be beats per second, right? So that's the answer to the first part of our question of what is the slope of the line. That is the numerical slope of the line, okay? The next part of the question is what does the slope represent? So that means we need to think about it a little deeper here. So if we go back and think, okay, well, slope is equal to the change in y over the change in x, as we have discussed. The change in y is number of beats, and the change in x is time. beats per second. So what is that? M is equal to heart rate. Okay, that's the information it's giving us. So when we look at this graph then, what we're analyzing is heart rate. Okay? Now we're going to do something really exciting. Well, one more thing and then we do something really exciting. So, what if it says, what is the average heart rate at 45 seconds? Well, average heart rate, this language, when it's saying average, that means slope / general trend. So it's not saying what is the number of heartbeats at 45 seconds. That's not what it's asking. It's saying what is the general trend, what is the average heart rate? Because heart rate, we said, was slope. So if you just went to your graph and went like, okay, 45, and then looked and saw what it is, wrong. Because it's asking what's the average heart rate. And average implies general trend. Okay? So it doesn't matter what time we're at, the heart rate, the average heart rate, is the same for every single time. Right? Because that's what slope is. Okay? So our answer has got to be, we know that slope stays constant, because that's what it is. It's a general representation of the whole trend. What's going on? Therefore, it's 1.07 beats per second. So now we're going to take it even one step further. We're going to take that linear equation and we're going to take our physics equation and we're going to stick them together. Okay? So write out the linear equation for this graph. So a linear equation is y equals mx plus b. What do we know about this graph especially now? We have solved for m. So now I'm going to take that and put it in. I'm going to put the actual number in there. Okay? So now I can say for this graph, y is equal to 1.07 x plus b. But what is my b? When x is 0, what is y according to our graph? It is 0, right? When x was 0, y was 0, because it went through the origin. Okay? So we can say, well, that is 0, so we can eliminate that from our equation and simplify it. And then we can say y is equal to 1.07 x. Okay? So we've simplified it, and now we actually have a linear function to represent this data. So, what is the point of that? Okay? The point is, now, any time that you want to know what their the number of heartbeats that they're at, or any heartbeat they're at, you want to know what time it is, you can just put it into that formula, and you got it right away. One calculation done. You don't have to do another experiment. Because if slope stays the same, for that experiment, you can just plug in the data. Okay? You don't have to do it over and over again. Okay? So now, it's saying, what would be the average number of heartbeats in a time period of 175 seconds? Is this interpolation or extrapolation? So, what's it saying? It's giving us a new time, and we want to figure out what is the average number of heartbeats at that time. Okay? So, what is time? Is it an x or a y value on this graph? X. So we are told a new variable. We are told that x, actually I'm going to use green instead here. We are told that x is equal to 175.0 seconds. If I'm trying to figure out beats, that is my y, okay? So I'm trying to find y. That's my question. And I know my m, because I found that out already. So m is equal to 1.07. So now I get to just put this into my formula. Y is equal to 1.07x. I'm solving for x. I'm going to use my colors. It's more fun. Okay. Now I can plug in for x. So now y is equal to 1.07 seconds times by 1.07 beats per second times by 175.0 seconds. Watch this. Your units for seconds can cross off now. And you're left with, so all you got to do is put that into your calculator now. What we got? 187.25. What are my units? Beats, because those seconds crossed off and that's what I was left with. Okay? Sig digs now. So you go, oh, this is a crappy example because our data. Oh, know what we do for our sig digs? Let's look at this sig digs. Okay? How many sig digs there? 4. Yes, indeed. So 187.3. So we round up. And that is our answer. Okay. So,